Okay, welcome everyone. Thank you so much, Nina, for waking up super early to join us. Nina's going to be talking on fusion products of twisted modules in permutation orbifolds. Feel free to start whenever you're ready.
Okay, thank you. Let me put it full screen. Okay, so first I would like to say thank you very much for the invitation. And today I'm going to talk about fusion products of twisted modules in permutation orbifold. And in particular, I will talk about our recent result about fusion products of twisted module with twisted module in permutation orbifold. And so here's the outline. So first I will talk about the motivation of studying this topic and also recall some basic notions that I need to use in this talk. And then in the second part, I will talk about the definitions of fusion products of twisted modules and some properties in general setting. And in third part, first I will talk about our result about 2 years ago with Dong, Li, and Feng about fusion products of twisted module and untwisted module. And then finally, I will talk about our recent result about fusion products of twisted modules with twisted modules in permutation orbifold. Okay, first I'm going to fix the VOA. Let me see how to put this. Okay, so we will still use this VY1 omega to denote the VOA, and G is going to be a finite group, subgroup of the automorphism group. So when we consider the fixed point set, we are going to write this as V to G, which is the set of the fixed points under the automorphism group. And we know that this also has a VOA structure, and this is called orbifold VOA. And so in orbifold theory, we want to study this VOA, and we also want to study the relation between this VOA and B. And this is a so-called orbifold theory. And orbifold theory is very important. For example, we know that the famous moonshine VOA is the first example of orbifold VOA. In orbifold theory, there is a conjecture says that if V is rational, then the orbifold is also rational. And so far, here this rational means that the ungradable V module category is semi-simple. Ungradable V module is also called admissible V module. About the conjecture, so far the known result is that first is by Kanahan and Miyamoto in 2016, they proved that if V is a rational C2 cofinite, G is solvable, then the conjecture is true. So this is regular and G is solvable, then the conjecture is true. And in the meantime, Dong, Ren, and Xu proved that if the orbifold is rational, then any irreducible module for the orbifold occurs in an irreducible G twisted B module for some G in G. And here, this G twisted module is some kind of module that is more general than the ordinary B module. So if you look at the vector space, so there is a fractional gradation, which is related to the automorphism, the order of the automorphism of this G. This is a so-called G twisted B module. And in particular, if we take this G to be the identity map, then you can get a notion of ordinary B module. This is the so-called, of course, it should satisfy some other conditions. And this is a so-called G twisted B module. And here, the C2 cofinite means that the certain quotient space is of finite dimension. Sorry. Okay, so the main feature in orbifold theory is the appearance of the twisted modules here. So you see that we say that in orbifold theory, we want to understand the module category for the orbifold. But if VG is rational, any irreducible module for orbifold occurs in an irreducible G twisted B module. So you see that to have better understanding of the module category for the orbifold, we should have better understanding of the G twisted B modules here. And now let's look at the fusion products for B modules. It's well known that if B is rational, then there are only finitely many irreducible modules. If we denote them by M0, M1 to MD, then the fusion product exists. Then one can write down the, this also can be called the tensor products. This can be written as a direct sum of the irreducible modules here. And here, this number Nijk represents the multiplicity of the irreducible module Mk in the tensor products of this Mi with Mj. And those numbers Nijk are called fusion rule. So the fusion products, and original definition is by the dimension of the intertwining space of a certain type. And this is the fusion products for the B modules here. And in orbifold theory, we actually want to, and sometimes if you know the tensor product of the B modules here, we want to see the relation between the tensor product of twisted modules with the tensor products of such B modules. Now we are going to denote CB, the category of ordinary B modules, and CBG is the category of ordinary modules for the orbifold. And it's well known that if B is rational, simple C2 cofinite BOA of CFT type and is self-dual, then the module category is a modular tensor category, which means that it satisfies many nice properties. It's a semi-simple, rigid, braided tensor category with finite number of simple objects and satisfying some non-degeneracy condition. And here the conditions is simple, rational C2 cofinite and CFT and self-dual. Those conditions are actually natural. Here, this rational C2 we mentioned this, and CFT type just means that there is no negative weight spaces, and homogeneous space of B1 is one-dimensional. And self-dual means that B is isomorphic to its control gradient module B prime. And many familiar examples satisfy the conditions here. So those conditions, yeah, I think in many papers, those conditions together is called a strongly rational. So you are going to see this sequence of conditions many times in this talk. And sometimes we will just say that the BOA is nice enough so that you can use all the properties here. So we mentioned that in orbifold theory, we want to understand the module category for the orbifold. And as we mentioned, because each module, when this VG is rational, you see that every module for this orbifold occurs in certain twisted module. So you see that to understand the fusion products for the orbifold BOA, we need to understand the tensor products for the twisted modules. So this is the motivation of studying twisted fusion tensor products of twisted modules in orbifold. Now let's look at the definition of S matrix here. So later I will need to use some entries from S matrix. So let's assume that V is a BOA of central charge C, and M is a B module with the lambda as a conformal weight. And for any homogeneous element, one can define a trace function associated to V, and we denoted this by G and V tau. And here, this tau is some element in the upper half plane. And here, this is the trace of this operator OV and QL0 minus C over 24. This OV is the degree 0 operator. And this Q, the relation of this Q and tau is that Q equals E to 2 pi I tau. This is the trace function of this one. In particular, if we take V equals 1, then the vacuum vector of this BOA, then the corresponding function, we say that this is the character of this M. And if if the VOA satisfies certain finite condition, then this converges to some holomorphic function. And another thing I should mention here is about the second VOA structure, which is given in Drew's paper. So we know that there is a second VOA structure associated to a given VOA. So we are going to denote this VOA by the operator denoted by this bracket here. And the omega, the conformal vector, we are going to use this notation. So the operator and the relation of the new operator and the original operator is this one, is this equation here. And so when we say, so later you will see the notion of the notation of this one. So when this V is a homogeneous element in the second VOA structure, then the weight is denoted by this notation. This is weight bracket V. This means that V is homogeneous in the second VOA structure instead of the first one. Now I can give you the definition of the S matrix. So it was proved in Zhu Dongli Mason's paper that the trace functions satisfy the following transformation property. So we still satisfy that it's a simple rational C2 cofinite, and we denote all the irreducible V modules by M0 to MD. Then when we consider the transformation of the trace function, it can be written actually for this kind of trace function, it can be written as the linear combination of the trace functions of the irreducible modules here. And you see that here, this Sij, so this, those numbers actually Sij form a matrix. This is called S matrix of the VOA, and it's independent of the choice of V. So later you will see that when we try to find the fusion products, it can be written as the S matrix here. Now here is the famous Verlinde formula. So we still, it actually tells you that the S matrix diagonalizes the fusion matrix. So we still assume that V satisfy all the nice properties, and S is the matrix. And in particular, we are going to use the first and the third property here. So the first one tells you the inverse matrix of the S matrix. The relation of the inverse matrix with the S matrix here. So here, the inverse matrix, the Ij's entry is given by this one. Here, this J prime means the control gradient of control gradient module of the module Mj. So M1 to Mj is still the notation we have seen before. And the third one actually tells you that when you consider the tensor products of the irreducible modules, the fusion rules actually can be written in terms of the S matrix here. So those are the two main conditions that I need to, two main results that I need to use later. So you see that under those conditions, the S matrix is invertible. This is important for us later. This is the Verlinde formula. It was conjectured by Verlinde and was proved by Huang. Okay, now here is a Cotton dimension of modules for VOA. So Cotton dimensions was introduced by Dong Jiao and Xu, and it was defined. So suppose that the trace functions, the trace functions GV and GN exist, then the Cotton dimension of M over the VOAV was defined by the limit of this one. And this is the original definition of Cotton dimension. And it has, well studied in Dong Jiao and Xu's paper. So we just assume that V satisfy all the nice conditions. And this irreducible V is still denoted by those ones. Then it was proved that the Cotton dimension of each irreducible module is of finite dimension. And in particular, you can write down the Cotton dimension in terms of the S matrix here. And we will use the Cotton dimensions, but in terms of the S matrix here, we are going to use those numbers here. This is about a Cotton dimension. Okay, now here are some notions from category. So first is about a fusion category. A fusion category is a category that is k-linear semi-simple rigid tensor category with finitely many isomorphism classes of simple objects and finite dimensional spaces of morphisms, and such that the unit object is simple. And semi-simple means that every object can be written as direct sum of simple objects, and rigid means that each object has dual. And notice that for a fusion category, there are only finitely many isomorphism classes of simple objects. And we say that a fusion category is braided if it's equipped with a natural isomorphism of the tensor products here. There is a naturalizer, so there is a braiding here, satisfying a certain condition. We are mainly going to use the fusion ring of a given fusion category. So if we assume that C is a fusion category, then there are only finite many inequivalent simple objects, and we write them as x1 to xn. Then associated to this fusion category, there is a fusion ring that can be written as this of C, and the basis element is given by the simple objects here, and the products given by the tensor products. So here, those A, I, J, K is just the fusion rules. And this is called a fusion ring. And it's well known that if you are given a fusion category, then the corresponding fusion ring is a semi-simple associative algebra. And in particular, if this C is also braided, that means if you are given a braided fusion category, then the corresponding fusion ring is a semi-simple commutative associative algebra. And this is the case that I will need to use later. So later you will see that we will find a braided fusion category, and we are going to consider the representation of the corresponding fusion ring. Okay, so from now on, we are going to always assume that the VOA we are considering is rational, C2 cofinite, CFT type, and self-dual. And in particular, we are going to consider G that is a finite abelian automorphism group. And actually, we are going to consider the case that G is generated by certain element. So it's a cyclic group. So it's an abelian group. Now, recall that we have a notation for the category of V modulus and category of the VG modulus here. Then you see that under the conditions here, both this CB and CBG are modular tensor category. So this CBG is a modular category. In particular, of course, it's a braided fusion category. Now let's recall a result from Kirillov and Ostrich's paper. So there's a notion of algebra in braided tensor category. So given a braided tensor category, and there is a commutative associative algebra that's defined in this category. So it's an object that satisfies certain conditions like associativity, commutativity, and units condition, and so on. So it's some kind of algebra in a braided tensor category that satisfies some conditions. Then we say that this is a commutative associative algebra in the sense of category. So this is different from the usual sense when we say that an algebra like VOA. And it was proved by Huang, Kirillov, and Posky that the VOA V is actually a commutative associative algebra in the category CVG. So this is CVG is of course a braided tensor category, and they prove that actually as an object is this CVG is satisfying the conditions here. So this is a commutative associative algebra in CVG. So this V is an algebra in as an object in the category. And later we are going to consider the representation of this V as an algebra in the category. Now here this result is from Kirillov, Ostrich, and also Christic and Canada and Macquarie. So if we denote this RAP-V, the subcategory of the subcategory of this CBG, this category, which consist of every BG modules together with some intertraining operators satisfying some conditions like associativity and unit condition. So this is the RAP-V, which is a subcategory of this one. And so actually this RAP-V is the module category of the algebra we just mentioned, the algebra in the category. And it was proof that, so first it's obvious that there is a categorical tensor products functor, which is associative in this category. So if you consider this category, there is this tensor product functor, and this itself is already associative in the sense of the category. And this result is from this paper. So this RAP-V is a fusion category. And the third thing, if we notice here, we are considering the case that G is a G is an abelian group. So you see that the RAP-V is also braided. So we have this RAP-V, which is a braided fusion category. So now if we consider the fusion ring of this braided fusion category, as we mentioned earlier, this is a this fusion ring is a semi-simple commutative associative algebra. This is the result that we are going to use later. Okay, so those are basic notations and no result that we need to use in this talk. Now let's look at the definition of tensor products for twisting modules. So it was defined by Xu, Dongli, and Mason Huan. If we consider tensor product twisting modules for in the sense of VOA, so it was defined the tensor products of two twisting modules, M1 and M2. This M1 is a G1 twisting module, and M2 is a G2 twisting module, and G1, G2 equals G2, G1. So the G1, G2 are commutative automorphisms. And so the tensor product of the two twisting modules is defined as a G1, G2 twisting module, and such that the intertraining operator satisfy certain universal properties here. And this is the tensor products in the sense of BOA. And we are going to use this notation to denote the tensor product in the sense of BOA. So we use the superscript here to denote the tensor products in the sense of VOA. And I think in the previous slide here, we used the subscript here to denote the tensor products in the sense of category. And in the sense of category, this is associative already. But from the definition of the tensor product of this one, we don't know whether this is associative. But actually later we prove that if you consider because we prove that actually if you consider G1 twisting module M1 and G2 twisting M2, so those twisting modules actually are objects in the RAP-V. And you know that in RAP-V, the fusion products exist in RAP-V and it's associative. So by this idea, in 2019, we were able to prove that actually if you consider tensor products of two twisting modules, no matter it's in the sense of BOA or in the sense of category, actually they are isomorphic. And because in the sense of the category, the tensor product is associative. So of course, in the sense of BOA, the tensor product is also associative. So we obtain the associativity of the tensor products of twisting modules. That's the result that we have obtained in 2019. Those are the general results we have so far. Okay, now let's look at the permutation orbifold. So we said that we want to study the tensor products of twisting modules in permutation orbifold. So you might have the question, why do we want to study this particular type of orbifold? So actually, the first reason is we know that in general, it's very difficult to construct twisting modules, but for permutation orbifold, we actually know the explicit construction of twisting module. This is the first reason. The other reason is that for any VOA, you can consider the tensor products and you can consider the permutation orbifold. So let's look at the permutation orbifold. So if you are given a VOA, you can consider the tensor products, and this is also a VOA. Now, if we consider sigma, which is an element in the permutation group SK, now sigma acts on the element in the tensor product VOA just by permute the 1 to k here. So this sigma naturally gives you an automorphism of this VOA, this tensor product VOA. Now, if we consider the tensor product VOA, this VOA under this group G, then this orbifold is called the permutation orbifold. So you see that for any VOA, you can consider the tensor products. So you always can have such a permutation orbifold. And the permutation orbifold itself also reflects the properties for the original VOA. So you see that it's not really that special type of VOA. So this is another reason that we want to study permutation orbifold. Now, about permutation orbifold, we mentioned that actually the construction of twisting module is clear already. It was given by Baron, Dong, and Mason. So in particular, they proved that if G is a k-cycle permutation, there is a one-to-one correspondence between the category of G modules for the tensor product VOA and the category of the V modules here. They actually also have a general result, like given any permutation, one can construct the corresponding twisting modules for the tensor product VOA. But because I only need to use the case when this permutation is a k-cycle, so I only give you the result here. So assume that M is an irreducible V module, then corresponding to this irreducible V module, there is a G twisting module for the tensor product VOA, and which will be denoted by this TGM. So later we are going to follow the notation here. So this TGV as a vector space is the same as the original irreducible V module, but the vertex operator here is different. So and there was delta operator involved, and the delta operator satisfying the conditions here. This is the G twisting module for the tensor product VOA. And conversely, if you are given a G twisting module for a tensor product VOA, one can also construct an irreducible V module. So there's a one-to-one correspondence here. The construction of a twisting module is very clear. So we know that if you consider irreducible modules for the tensor product VOA, those can be written as M1 tensor, M2 tensor, MK, and those MIs are just irreducible modules for this V. This is what untwisted modules for the tensor product VOA look like. And in 2019, we consider the fusion products of untwisted and twisted module. And so we still assume that V satisfy all the nice properties. And we were able to prove that actually, if you consider tensor products of an untwisted module and a twisted module for the tensor product VOA, this actually is equivalent to the tensor products. The right-hand side M1 tensor, MK, and tensor N, those are tensor products for as V modules here. And once you, so those was will give you some V module, then the corresponding G twisting module for the tensor product VOA, that will be the result for the tensor products of the untwisted and the twisting module here. So from this formula, you can see clearly what's the relation between the tensor products of untwisted and twisted module and the tensor products in SV modules here. So this is what we have obtained so far. So our goal for tensor product, twisty and twisty module is still the same. We want to have a straightforward formula that can tell you the relation between the tensor product twisty modules and tensor product of the original modules here. So in particular, what I need to use here is the case that if we take M1 equals M and other modules to be the M0, those V is just M0. And if you consider this case, you see that actually any G twisty module corresponding to this M can be written as the tensor product of this untwisted module and the twisted modules here. So left hand side is tensor product for tensor product VOA, and right hand side here, this here, those are modules as V and V modules, and I'm going to use this one. Okay, now let's consider fusion products of twisty and twisty modules. And notice, I should go back here. Notice that here, this K can be any K. And this K can be any positive integer. And as long as this G is a K cycle, then we have this formula. This is the result we have earlier. Now, you will see that actually now I can only consider this is sigma, that is a P cycle. P is a prime number. This is different from the previous case. The reason is that we are still working on this program, and we believe that we still can get a case when sigma is any K cycle. But for now, we only have this result. So far, we only have this result. So this sigma is a P cycle. The good thing about this P cycle is that because now we are considering the group that's generated by this P cycle. P is a prime number. So you see that any elements in this group sigma to I is still a P cycle. If this P is not a prime number, then sigma to I might be written as this products of disjoint cycles, which can make the calculation more complicated. So far we only have this result. Okay, so we still assume that M0, M1, MD are the set of all the inequivalent irreducible V modules. Now we are considering the permutation orbifold. So it's the tensor product VOA V tensor P under this G. G is the cyclic group generated by this sigma. So of course this G is a billion. Now we want to consider fusion product twisty and twisty modules. So we say that because any sigma is still a cycle, right? So now any twisty module can be written in this form. This Mi and Mj are just some irreducible V module. So basically we want to find out a formula for the twisty module and the twisty modules here. So this is our goal. And notice that in the previous slide, we mentioned that actually, as long as this G is a cycle, then any G twisty module correspond to this M can be written as tensor products of this here, of the untwisted and the twisty modules here. So if we replace this part by this one, by the previous property, then you see that actually the twisty module can be written as this tensor product untwisted and the twisty modules here. Now you see that actually then by associativity of the tensor product, we already proved the associativity of the tensor product already. By the associativity, you see that actually to find out this one, we only need to find out the tensor product of T sigma SB and T sigma TB here. This is so we only need to find out this one. And notice that we know that if you consider the tensor product G of G twisty module and H twisty module, if G and H are commuting, then you see that the result should be G H twisty module. This is general philosophy. So you see that the tensor product of this result should be sigma S plus T twisty module. And notice that this S plus T should be understood as modular P. And of course, this S plus T cannot be equal to this P. So this should be still some twisty module. So so first we know that the tensor product of the two twisted module should be able to be written in this form. And now we only need to find out the numbers, the nj here. So our goal is to find out those numbers nj. So now let's see how to find out the nj here. So let's recall that now we are considering this permutation orbifold, and we know that if you consider the corresponding modular tensor category, you see that this V tensor P also can be considered as a certain algebra in corresponding modular tensor category. So we still have the definition of this wrap V tensor V, and this V tensor P is still considered as an algebra in the corresponding category. And this is wrap V tensor P. We can use the result we mentioned earlier, and this is a braided fusion category. Our G is still abelian, so this is a braided fusion category. So, and also all the simple objects in this wrap V tensor V, all the simple objects here are just all the irreducible twisted modules for the tensor product VOA. So all the simple objects can be written here. Those are untwisted modules, and those are the twisted modules. So we have all the simple objects for the wrap V. And now if you consider the fusion ring of this braided fusion category, then we know that it's a semi-simple commutative associative algebra, and the basis element is given by the simple objects here, which are given by those here. And in the meantime, we also know that by Dong, Zhao, and Xu, and the quantum dimension of the untwisted module is given by this one. So earlier I gave you the quantum dimension for irreducible modules here, and quantum dimension for the tensor product here is actually just the products of the quantum dimension of the Mij's here. So this is the quantum dimension of the untwisted module. And we also know that the quantum dimension for twisted modules, which is given in Dong, Ren, and Xu, it can be written in terms of S matrix. This is a quantum dimension for the twisted modules here. And one should also notice that when you consider the quantum dimension for the twisted modules, you see the numbers here. This is independent of the I here. So for any, no matter it's a sigma twisted module, sigma square twisted module, the quantum dimension is always this number. In particular, if we consider the quantum dimension of T sigma B, so that means we can M0, then you will have this is S00 over S00 to P. So the quantum dimension for T sigma IV is this number. And we will need to use this. Okay, so I mentioned earlier that now the corresponding fusion ring of this wrap B tensor P is a semi-simple commutative associative algebra. So you see that if we consider the representations, the irreducible representation should be one dimensional, and we actually can define of K such that the simple objects in this wrap V tensor K is defined, it's mapped to this one. The twisted module is mapped to this number, and this K goes from 0, 1 to D. And for we actually can prove that for each K, this of K give you an irreducible representation of the fusion ring. So the basis elements of the fusion ring are those ones, and twisted module is mapped to this number, and this is mapped to this number. So we claim that each of K is irreducible representation. Now let's see why this is true. So when we say that if this of K is irreducible representation, then that means when you consider the tensor products of the elements here, so in this fusion ring, then you see that those of K should preserve the tensor product. So in particular, if we consider the tensor products, we were considering this is T sigma SV tensor, this is T sigma TV. So if this of K is really a representation, then you see that here the representation should preserve the tensor products here. And we say that this is mapped to T sigma SV, it's mapped to this number. So that's when the case J equals 0. So this is SK0, SK0 and P. So you will get this number here. So this is the first one. And the second one, this give you this SK0, SK0P. And it preserves the products, the right-hand side. We also have the number of this one that equals this one. Now, if you simplify the equation here, then you will find that finally this equation can give you the corresponding equation here, and this is NJ N0 to ND are the numbers we want to find, and the coefficient is actually just SKJ, and here left hand side you have this. Those are entries from the S matrix of the VOAB. So you see that actually if you consider N1 to N0 to ND as unknown variables, and you see that the coefficient matrix actually is given by the S matrix, and we know that now for the VOA we are considering the S matrix is not degenerate. So of course we can find out the solution. There's a unique solution for those NJ. This should be NJ. So we can find out those NJs. So now actually you can write down this NJ in terms of the S matrix here. So we were able to find out the formula, this NJs here. So you get the tensor products for the twisting module and the twisting modules here. So we were able to find out the NJs here. You see that those numbers NJ are just in terms of the S matrix here. So which is just the information from the original VOA. So this is what we have obtained so far. Now the next question, of course, is that what if this is sigma is not so we mentioned that this is sigma is a p cycle, p is a prime number, so that we can make sure that here right hand side when you consider the tensor product of sigma S twisting module and sigma T twisting module, the result should be of this form. But what if this is sigma is not a p cycle? For example, if we consider G is any k cycle and k is any positive number, then when you consider this tensor prop of the G twisting module and the G twisting module, and in general we know that this should be equals some G square twisting module. But what if this G square can be written as products of this joint cycle? Then in that case, that will make the calculation much more complicated. And yeah, this is the next question that we need to consider, and we still need to do more calculation to get a formula for this case. And yeah, I think that's all for my talk. Thank you.
Thank you so much, Nina.
Thank you.
Thank you. Are there any questions for Nina? Please feel free to unmute yourself and go for it. So I have a question, Nina. You mentioned that you could do this for very nice DOAs, right? Strongly rational or CFT. Do you have any expectations of what would happen if you were to drop? I guess you wouldn't have modularity and a lot of things that you've used, but you still have S matrices in less nice DOAs sometimes, and they are non-degenerate in some way. They're not finite, I guess. Do you have any expectation of what could happen in that setting?
I don't know. For if the VOA is not that nice, then I have no idea what they'll look like.
Any other questions for Nina? Okay. If not, let's thank Nina again. Thank you so much, Nina. Thank you for joining us so early.
Thank you.
Let me stop recording.